Before I begin my example, I'd like to quickly review the fundamental theorem of line integrals. This theorem says that if you have a conservative vector field, capital F, and of course that means that there exists some scalar valued function little f, such that big F is the gradient of little f. So if you integrate a conservative vector field over some smooth curve C, and let's say that that curve begins at some point P and ends at some point Q. The theorem says that the value of this integral is equal to the potential function evaluated at the endpoint minus the potential function evaluated at the beginning point. Now this is interesting, and it's nice because what it allows us to do is evaluate the line integral without parameterizing the curve. If the vector field is conservative, if it has a potential function, then the value of the integral can be obtained by evaluating the potential function at the endpoint and then subtracting the function evaluated at the beginning point. So let's go ahead now and apply this. So here we have a line integral in differential form. The associated vector field looks like this. The first component function is the function m of xy equals 2xy plus 2, and n of xy equals x squared. Now we're going to evaluate this line integral over 4 different curves. Before we can use the fundamental theorem of line integrals, we have to make sure that this vector field is conservative, and remember that the test for determining if a two-dimensional vector field is conservative is that n sub x must equal m sub y. So let's check that, make sure that that's true. If it's not, then we can't use the fundamental theorem. Well, n sub x is 2x, and m sub y is also 2x. So we know this vector field is conservative. So let's find a potential function. By definition of conservative, there exists some function little f whose gradient is big F. And of course that means that f sub x equals 2xy plus 2, and f sub y equals x squared. So let's start with this equation. Let's integrate with respect to x. What we get is x squared times y plus 2x plus some function of y. Let's call it g of y. If we take the second equation and integrate with respect to y, we get f of xy equals x squared y plus some function of x. Let's call that h of x. Now what we have here are two different representations of the same function. So we put the pieces together. Notice what's common is the x squared y. And then we have plus 2x. That matches the h of x over here. And then g of y could be some actual constant. We might as well just let it be 0. So here is a potential function for this vector field. And let's just check this really fast by taking the gradient and make sure that we get the vector field. F sub x is 2xy plus 2, and f sub y is x squared plus 0. And notice that that is what we started with. That is our vector field. Okay, let's get rid of all this stuff. Okay, so unfortunately I also got rid of the potential function, so let me put that back on the screen. It was x squared y plus 2x. Okay, so in part A we're integrating over a semicircle. The semicircle y equals square root of 4 minus x squared. It begins at 2, 0 and ends at negative 2, 0. What the fundamental theorem of line integral says is to get to evaluate this integral, all we have to do is evaluate our potential function at the endpoint and subtract the potential function evaluated at the beginning point. Well, f of negative 2, 0, look at the y-coordinate, you'll notice it's 0, so that's going to be 0 plus negative 4 minus f of 2, 0. Again, the y-coordinate is 0, so the first term is going to be 0. And the second term is going to be 2 times 2, which is 4. So the value of the integral over the semicircle is negative 8. In the second part, we're integrating over a different curve, the portion of the parabola y equals x squared, from negative 1, 1 to 2, 4. The value of that integral is going to be the potential function evaluated at the endpoint minus the value of the potential function at the beginning point. What is f of 2, 4? Well, 2 squared is 4 times y is 4 plus 2 times 2. So it's that minus negative 1 squared is 1 times 1 plus 2 times x, which is negative 1. So what is that? That's 20 minus 1 plus negative 2 is negative 1. So the value of that, the integral over that curve is 21. Let's take a look at the next part. In this case, we're integrating over an ellipse. It says it's oriented clockwise, but that's really not going to make any difference. The thing that's important here is that the curve that we're integrating over is closed. You can think of it Just pick some random point on the ellipse, call it P. You can think of it as beginning and ending at the same place. So the beginning point, the end point are the same. Like it says, it's oriented rather clockwise, but that's not going to make any difference. Because when you evaluate the integral using the fundamental theorem of line integrals, since we're thinking of the curve as beginning and ending at the same point, what that amounts to is evaluating potential function at p and subtracting f of p. Begins and ends at the same point. And of course, that gives you 0. And that's something that's interesting about the fundamental theorem of line integrals. One of the things that it actually tells us is that when you integrate a conservative vector field over a closed curve, the value of the integral is going to be 0. Okay, so let's look at the last part. It says we're integrating over some smooth curve beginning at 1, 2, and ending at 3, 1. So it could be any curve. Oh boy. Okay, let me get rid of some of this stuff. And it's gone. Okay. So we're integrating, in the last case, over some smooth curve beginning at the point 1, 2 and ending at the point 3, 1. And this kind of sort of captures the spirit of the fundamental theorem of line integrals. The point is, when you're integrating a vector field, which is conservative, over a curve beginning at some point P, ending at some point Q, it doesn't matter how the curve actually gets from point P to point Q. It could take a straight line path, it could wander around a bit. The value of the integral simply depends on the value of the potential function at the end point and the beginning point. So let me move this a little bit. In this case, the beginning point is 1, 2, and the ending point is 3, 1. So the value of the integral is going to be little f of 3, 1 minus little f evaluated at 1, 2. I'm going to pull that down a little bit. There we go. F of 3, 1 is 9 times 1 plus 2 times 3. Again, I'm using this function here. And f of 1, 2 is 1 times 2 plus 2 times 1. So what is that? That's 15 minus, looks like 4, which is 11. And again, it doesn't matter how the curve gets from 1, 2 to 3, 1. The value of the integral is going to be 11 regardless. So that's basically what you need to know about the fundamental theorem of line integrals. Just remember you can only apply it when the vector field is conservative.